Hi, I'm Gary Hughes from Cal Poly in San Luis Obispo. I collaborate with Phil Lubin from UC Santa Barbara. We're about 100 miles apart, so it's a nice, easy collaboration there. I've been working with Phil on several projects, among them the D-STAR program, which envisions an orbiting array of lasers to do planetary defense and other things. One of the additional benefits of having a space laser might be molecular composition analysis of distant targets, and that's what I'll talk about here today. Our NIAC proposal was a system that's envisioned to do molecular composition analysis of cold solar system targets, like asteroids and comets and planets and moons from a distant vantage, like, for instance, if you're orbiting that object, orbiting the target. And so the vision is to have some laser system there that's producing a directed energy beam at the target. It would heat that target and evaporation would occur. Evaporation materials would form a plume of material right in front of the target. And then, in kind of a twist to some of the existing spectroscopic studies, we would use the heated spot as a backlight to the spectrometer and try to view absorption lines. Now, this depicts characteristic absorption in optical wavelengths, and we're more in an infrared regime. We'll talk about that in a second, each of these subsystems. But if you heat the target, the infrared energy passes through the target and back to a spectrometer on board the spacecraft, which would then do infrared spectroscopy. And so we try to give all these things a name, right? Here's mine. Remote laser evaporative molecular absorption spectroscopy to, in some sense, differentiate it from some other things that are out there. So I'll talk about the subsystems individually, but let's first talk about a comparison, thanks to Ariel for spurring us into thinking about how these things might compare to other systems that are out there. LIBS, laser-induced breakdown spectroscopy, is currently equipped on the Mars Science Laboratory rover, the ChemCam. And so the depiction here is that a laser is pointed at the target, and that laser is about 10 terawatts per square meter, sufficient to dissociate molecules and ionize atoms, and that ionization then would produce characteristic emission. And you can look at that characteristic emission with a spectrometer on board the spacecraft, right? Standoff distances for the Mars rover are 7 to 8 meters or something at the most. But you could probably envision the same system at larger standoff distances with a better laser or something. But one of the keys here is that this is optical emission spectroscopy, slightly different than what we're proposing, right? The next one that I want to compare to, and there's probably lots of comparisons that we could do, but Temple 1, right, the deep impact mission, sent an impactor into the comet. That impact produced about 10 to the 6th kilograms of particles, mostly in the 10 micron range, 10 micron size range. And then they used the Spitzer Space Telescope at 3/4 of an AU to look at the mid and long wave infrared emission spectrum of those particles, right? So those particles were at a certain temperature. They were emitting infrared energy, and the spectroscope on board the Spitzer observed that plume, and both before and after the impact, and compared those spectra to do compositional analysis, right? And so this is at 3/4 of an AU. The LIBS was at 8 meters. There's similarities and differences to the system that we propose for both of those, right? So to put it in some sort of context, the LIBS is doing characteristic emission spectroscopy. The deep impact mission, the spectrometer aboard Spitzer, was doing mid and long wave infrared thermal emission spectroscopy. And what we propose then is absorption spectroscopy. The main difference between all of these methods is that these are doing emission from the substances that you're trying to explore. This one is doing absorption through the plume with a backlight that's created by that heated spot. So, we haven't really determined all about the, what advantages or disadvantages this might have. It's just a different way of doing things that might lead to some different capabilities in the future. So I'll walk through the subsystems as we envision for the phase 1 NIAC. So solar arrays would provide power to the laser array. And so we've done some preliminary design there that shows you can, for some sort of baseline system, you can fit this inside a 5-meter fairing, and you can see the laser array here and then the extensible solar panels there. And what's shown in the front and not mentioned here is that there's going to be some thermal management required, since there's inefficiencies getting the power from the solar array to the lasers. The next subsystem is the laser itself, and we're not really in this to do laser development, but if you give me a better laser, it can lead to a system with further standoff differences and maybe more capability, right? So one of the things that we envision is using fiber amplifiers that are currently somewhere in the range of 1 kilowatt per kilogram to put those into an array. And that array then would be, in one incarnation, coherently combined, and our modeling, is doing this coherently combined array. In another incarnation that's probably higher TRL at the beginning, we could do a tiled aperture emitter with just each of the emitters pointing to a spot adjacent to the next one on the target. In either case, we can use whatever laser that gets put onto the system. And then, in order to do our study for the phase 1, we wanted to do some optical modeling. And so, this is a nice, perfect system that's perfectly coherently combined. And then we introduce some phase perturbations that are either fixed or time varying. And we come up with our beam model, right? Our beam model. Now, the beam model, we need to do this to sort of do an end-to-end system simulation for what kind of absorption we're going to see from that spot. So the first step here is that optical model. Then the next thing is, what happens to all of that energy when it hits the surface of a target? So we've been working mostly with rocky targets, and so we created a circular bolide there of silicon dioxide or some other thing, and we used the output of the optical model and as an input to this thermal model for what happens when that thing strikes the target. Now, one of the big differences here between this and the LIBS might be this this flux requirement here, right? We envision about 10 megawatts per square meter, which is not sufficient to dissociate molecules, and it's not sufficient in general to ionize atoms. And so mostly what will happen here is ablation and evaporation, but the molecular constituency will remain the same. And so we can do molecular spectroscopy here rather than just atomic spectroscopy. And the 10 megawatts per square meter is going to be important because, because of phase change in the target, it's going to stabilize around 2,500 kelvins in a vacuum, right? 2,500 kelvins in a vacuum. Now, that's a maximum infrared emission at about 1.15 micron. Okay, so we'll keep all of those things in mind when we get to the spectroscopy. Our modeling suggests that, this stuff really quickly goes up and stabilizes to about, if you focus on the target, stabilizes to about 2,500 kelvins. Okay? So then, what happens when that energy hits the target? Well, we're going to have evaporation, and we need to try to predict that evaporation to see what kind of absorption we're going to get in that plume, right? And so, we use Langmeyer's equation, and we use the Antoine coefficients, and to do this, there's many steps, right? Many steps. And we can't go through all that mathematics here. I just wanted to put those two basic equations on the board to show you our general approach. But we have a couple of publications that describe step by step what our model is, right? What our model is to get that evaporation and absorption in the plume, okay? So I can't go through all of those here. We would take up way too much time. But if you're interested in those details, there's a little more information on the poster, but the publication that's there will walk you through step by step what we're doing. And this is the end result of that modeling, right, is, this is for an ice-bearing substrate, right? And so we use the model to predict what kind of absorption there's going to be across infrared wavelengths that are, at about 2,500 kelvins, right? And so you can see then oops, didn't want to do that. You can see the emission or the absorption here from an ideal radiator, and that absorption then can lead to some sort of detectivity or spectral analysis to tell us how much ice is there, right? And so, for instance, in this one particular simulation, we used a substrate that had varying concentrations of ice. You can see the red line and the red line that's up there. If it's, on the order, I think the red line is 1% ice, and so 1% ice is going to be tough to see in this scenario. Other scenarios, we could probably see it pretty easily. But by the time you get to 10% ice, right, the bulk composition kind of a thing, you can clearly see that the models predict we're going to see some absorption. And of course, 100% ice, we're going to see it very easily. Right? So that's the model. And what we've done so far is we've started with this optical modeling from the laser. And we've run that through what it happens to the target and a little bit about those plume properties. And then we've used those plume properties to determine this absorption profile that we might see at a spectrometer that's aboard the spacecraft. And so that's what we've done so far. Where do we go from here? Well, we need to get into the laboratory and do some experiments, and that's what we're going to hopefully do in phase 1. And so I've sort of sketched out some phase 1 goals here, which include continual theoretical development of our models and different cases and simulations to see different substrates and whatnot. It would be nice to have some sort of vision for how to get to TRL2 with this, right? What kind of experiments do we need to do in the laboratory? Now, we're already working toward a simple experiment here, right, for phase. This is going to be a phase 1 experiment, right, where we have a little vacuum chamber and a sample that's inside the vacuum space. And the laser beam comes through the window there, and it ablates that target, right? And it creates some sort of plume above that. And one of the biggest things about our model that the hardest thing that's going to have to happen here is that it'd be really nice to have this really big spot and a lot of flux. So a lot of stuff is coming off of there, so that you have a really bright backlight and a really thick plume, right? That's the ideal case, right? We're not going to hit that ideal case, but under certain scenarios, how big of a spot do we get, right? How big of a spot do we get? And how much absorption is there? I guess if I can go back one, I think, did we put that in there? Okay, so, here is this case is for 10 kilowatts of power, or 10 kilowatt laser, a 1 meter mirror. The radius of the spot is 1 millimeter, and we're at a distance of 10 kilometers, right? And so that's what this particular simulation was meant to do, right? But you can see, even with a 1 millimeter spot, we're doing pretty good here, right? And so, is that right? Okay, that's a question, right? This is theory. And so what we want to do with this particular experiment is maybe make some test of, what is the plume density here, and what kind of absorption do we get through that FTIR beam, or a laser beam through there to maybe do some density profiling in some sense. And so, we're working toward this as a phase 1 experiment, right? But this is a simple experiment, and it doesn't really test the idea of using a distant source. Right now, the experiment would use the glow bar from the FTIR as that back illuminated source. We're not really testing the idea of the back illuminated source yet, right? And so I don't think we're going to get there in phase 1. We just don't have the equipment. It requires some custom things, right? We're just working with the stuff that we have in the laboratory now. But so part of the phase 1 goal would be to execute some simple experiments to test the basics of our plume models, and then to try to envision and maybe design some experiments that would work going into phase 2 to try to figure out if the backlighted scenario is going to work well for us, right? And so another thing that we would like to do then is, in some sort of hypothetical mission context, to specify a system configuration for how this might go. Like, for instance, where's Lou? Can we put this on ARM, Lou? Can we put this on ARM? Right? We're almost ready. We are at TRL1, and we can talk about why, but the final report will definitely sketch a path forward, and I'm not sure, ARM might be a little ambitious. Now, I first had, so what the heck are we going to do with this system? We've talked about what the system is, but why would we want to put it there in the first place? And I initially had a methane spectrum there, for looking for organics. This is one thing that could happen, right, looking for organics. But somebody suggested that, it might be more profitable to look for substances that are addictive, right? So, I put caffeine and nicotine up here now, which we're probably not going to find on any asteroids, but the point is made that why is this going to be important to develop, right? To me, and probably to most of us here in this room, the first reason there, human curiosity is sufficient, right? But I'm not sure we can sell that and get funding for it on that basis alone. We can also add then additional objectives for our system. Let's look for ice or water for fuel or mission resources, organics, of course, and life origins. To me, all of those are singularly sufficient, but let's try a couple more. Planetary defense is definitely something that might catch the eye of funding agencies, right? The Chelyabinsk impactor shown there, unfortunately, that was a very spectacular event, but unfortunately, it's only about an 80-year recurrence time for Chelyabinsk, right? And so again, I don't think most funding agencies think that far ahead, right? But the last one there, a lot of people are starting to think about mining economic resources from asteroids, and in particular rare earths. For instance, 10 to 15 kilograms of lanthanum from China go into every Prius, right? And so there are many considerations there, perhaps, that might help pique the interest of funding agencies. And so that's my view of what the R-LIMA system might look like, and I'll take any questions you might have. Yes. Can we go on ARM, Lou?
Well, love to have it. But you didn't really explain. You said you addressed the question, but you didn't explain why you're doing this as opposed to using already existing laser emission experiments, which we have on Mars, which we've had on small bodies, and so I'm asking, what's the motivation for this approach as opposed to not using the others? You said you didn't want to go into those benefits, but I think you need to address that. And then I guess the other question is what's really TRL1 here? Is it the laser, or is it the trying to produce a spacecraft component, or it's certainly not the emission measurement?
Okay, so I'll answer your second question first. TRL1, because so far we've done some theory about backlighted spectroscopy in this standoff approach, right? We need to test that. There's nothing that's outside of TRL1 there, right? Now, equipment-wise, almost everything in the system is beyond TRL1. In fact, there's lasers on Mars, right? But the lasers that we envision are the fiber amplifiers, and to my knowledge, no one has flown a fiber amplifier in space, and no one has even really addressed the idea of rad hardening for fiber amplifiers. And so I would put fiber amplifiers at TRL1 squarely with much required experimentation to determine the path forward there. So there's at least two things that are TRL1 in our system.
So what's the motivation of doing it this way rather
right.
than the ones that
So I'll address your first question second. The Mars rover is, it's an amazing thing, right? It's crawling around Mars and shooting lasers at things, and autonomously nonetheless, right? But that's a complex mission, and it's an expensive mission, right? And if we rely on landing missions to determine the composition of things, then that's expensive and complex, and we probably could find some sort of middle ground between cost and science return if we do it remotely, right? That is, it's a whole lot easier to go up and orbit an asteroid than it is to land on one. And so, You know, in the first case, I would argue that this is a lot more cost effective than putting something on the surface, right? And as far as I can tell, you get pretty darn close to what LIBS is giving you, right? LIBS only gives you atomic composition, right? And we're not talking about atomic composition, we're talking about molecular composition, right? And so, you know, to me it gives you something that LIBS does not. You know, the other scenario that we use there, the Temple 1 impactor, right, the deep impact mission, you know, the spectra came from particles, right, that is 10 micron particles. And so, you know, the viewing was from, you know, 3/4 of an AU, but you don't get the same information that you would from molecular composition analysis with a backlighted source. And so I think part of the answer to your first question is that the motivation for this should be clear, at least some motivation should be clear initially, but I think also going forward we'll realize a lot of things that this will do that you can't get with other systems.
Jim Mantovani from Kennedy. We recently started working with a group of planetary scientists interested in making high-fidelity asteroid simulants, and we've made some at Kennedy. So if you're looking for some samples, we'll be happy to provide them.
Oh, you know, that'd be wonderful. You know, so far we've used various things like basalt, right? You know, trying to get some mimicry of things that we might see in actuality. I think we've put chocolate bars in there too, haven't we? Right. But yeah, it would be wonderful to have those kinds of things. Thank you. Yeah.
And hey, this is Bob Youngquist again from Kennedy. Just to reaffirm what you said, I mean, I've funded work in LIBS in the past, and it has its own niche. But being able to look at the vibrational bands and the rotational bands of molecules that you haven't broken down, you know, is something very important to doing spectroscopy. So I think this is a great idea.
Right, thanks.
Just wanted to affirm that.
So yeah, just along those lines, you know, at 2,500 kelvins, the maximum emission is around a little over 1 micron, and which is right there, you know, sort of well situated for low vibrational spectroscopy, right? So. Yeah.
Hi, Hi, Philip Lubin, UC Santa Barbara. We've never met before, but so I just want to point out to people that the same mission, which does molecular spectroscopy, actually is a planetary defense mission as well, which will take on a 100-meter or larger class asteroid. So it's also useful for other things, such as protecting life on Earth.